Jason, there's a bunch of breakfast stuff. Are you gonna take that with you?
Do you want to take a few?
No, like it's just like, what are you doing with it? If you're taking it, good to know.
I'll take some. I won't take all of it just because it's already too much stuff.
Okay, there are 3 grapes. I'll take 1.
Sure. One more thing, everyone. We have too much food. If you want to take some food, go for it. This one isn't mine, is this? Oh, okay then. Cool pen though. I'll put it there with anyone's. I think the stream is working. We'll start in just 4 minutes while I finish chewing this fried chicken sandwich. So everyone, feel free to take food. There's probably a lot of food left. I don't know who's gonna take all the food.
Oh, you were doing it like this? Pattern is like that. Yeah, you don't want to calculate this right. Can you make this calculation outside of this? Can you do that, for example, like 4 under 7? You're calculating for 7 numbers. Then it will be, this will be calculated for sure because you have like 100,000 for loops right there. For each of them, you have one. I gotta bring it back. So what I want to do is,
Oh, yeah, you gotta hold it so I can take it.
until whatever the right? And then calculate. But if you already have a number that you calculate for then just use it. You know what I mean? So I need you to recalculate this. So
What's your style, Paul?
the goal is to
I feel insulted in the way that you would insult a lamp.
That's fine. I don't care what number. I care about what one will give me. -1 or so basically you're calculating this.
I know. Who would do that?
You can do it all. You calculate 1 until 12. Right? Continue with 13. Continue with 13. I understand. So basically, this is 1, is it? -1. -1 over here.
Okay, we'll get started soon.
Oh, I see. So this is just that part.
Test, does this audio work?
Because
I don't know what any of these terms mean. I just solved the problem for loops.
Test.
You guys call it something.
Cool, okay. Audio's working.
Don't label my for loops.
And I will actually do an entire display capture.
you already have then your input here, you don't recalculate, just look at
Oh, oops. Second monitor.
that's one-time calculation. For each of the inputs,
Let's do like this.
which means you got my point, I hope, right? Okay.
It's like if I do this. Okay, I think we're good to start. Let's begin with a challenge review. So just like before, just like last SCPE, I'll be going through all the problems. Stop me if you have any questions, of course, but we'll go through all solutions for every single problem. We're going to start first on Clover picking. Let's go one by one. So how this problem works is like this. We're given an array. It'd be 10, 11, 12, 13 for this one. And we have to find the subarray, which has the maximum sum, but we have to find the subarray with the same parity. That means all elements have to be odd or all elements have to be even. Because how this thing goes is like, clovers are lucky, but if we mix together clovers that have different parities of leaves, you have an even-numbered clover leaf inside a bunch of odd clovers, then it's very unlucky. And we want to get as much luck as possible. So we have to find, let's say we're given this one, our possible subarrays that are of the same parity. And subarray means it has to be contiguous, which means you cannot have like gaps in the array. I cannot pick this 11 and 13, oops, and 13 to be in the same subarray. It has to be either 10, 11, 12, or 13 as our subarrays. For this second test case, you can either do as a 7, 5, 5, you can do a 4, you can do a 5, an 8 and a 10, because you have the same parity, they're both even, or this 9. Does that make sense to everyone? Any questions on that? How we code this one, I'm just going to copy this 7, 5, 5, 4, 5, 8, 10, 9. I'm not going to remember that. So we have that 7, 5, 5, I already forgot. Let's see. 4, 5, 8, 10, 9. 4, 5, 8, 10, and 9. That's our starting array. And we have to find each of these subarrays that have the same parity, which I can highlight. We could do this one. Is that fine to see? It's a little bit sharp. Or we can do this one. Or we can do this one. We can do these two. Or just this one. Right? Does this make sense? Because each of those have the same parity. They're either all odd or either all even. What we could try is a double for loop. Maybe we can try like a starting at this one. How far can we go before the parity switches? Maybe starting at this one. How far can we go before the parity switches? Does anyone know why that's a bad solution that we shouldn't do? Double for loops are generally not good to have in our code because I'm starting here. In the case where I have like something like this, 1, 1, 1, 1, 1, 1, all the way to 100,000 ones. That will have us do one of these loops. We'll go 100,000 times. The next time I do a loop, I have to go 99,999 times. Next time I go, I have to do 99,998 times. That's very, very slow because there's so many things. And that ends up being approximately 10 to the 5th times 10 to the 5th times divided by 2, which is like 5 billion. Computer's not going to be able to do that. So what we could do instead is, I don't know the official term for this. I like to call it accumulation of an array, where we start at the beginning, go forward until we can't anymore. Let's say we go forward. Our accumulation right now is accum equals 0. We go here, our accumulation becomes 7. We go here, our accumulation becomes 12. We're just, as we go, we're adding numbers down to this one. As we go here, our accumulation becomes 17. As we go here, though, we have to reset our accumulation because we found a different parity. So now our accumulation becomes 4. Over here, just like before, we have to reset. Our accumulation becomes 5. We reset again, it becomes 8. We do not reset this time because it's the same accumulation, same parity, which becomes an 18. And here, which becomes a 9. So how do we code this one? We can do this one using just a simple for loop, going through each of these digits. We will have to make a few variables at the top. We have to first make a variable called best, which keeps track of the best one we've seen so far. Best will start at 0. Accumulation will start at 0. And how about we make like a current parity? How about we just start it off as 0 as well, might as well. How our code is going to go is I'm going to call this one my array. We're just going to go a for loop for this one. I'll be writing this one in Python because generally Python is very, very similar to pseudocode. and it's pretty easy to read. But of course, feel free to code this one yourself in any language of your choice. I'm gonna do like this. And how the syntax goes like, for every element number inside that array, I'm gonna go like this. I need to first check if it's even or odd. So I'm gonna do my N-P, I'm gonna call it my new parity equals in modulus 2. What this one does is the modulus is the remainder. You can see what's the remainder of n divided by 2.
Do you want to use this for next SCPE? Just like your stuff, or did you want to start?
Can you put that one inside the drawer over there? Yeah, thank you. So I'm going to do like this. If my n is odd, this is going to become 1 because any odd number divided by 2 has a remainder of 1. And any even number divided by 2 has a remainder of 0. So we're going to say if my new parity matches my current parity, we're going to increase the accumulation. So accumulation, plus equals the element in. And we're also gonna say, that's it actually. What about the else case? When the new parity does not match the current parity. In that case, we're gonna do like this. Parity equals new parity. And then we're also going to do accumulation. We're resetting the accumulation to the current element. Not 0, we're resetting to the current element. Because you're on an element, you have to add it to your accumulation. What else do we have to do here? After these two statements, we also have to do the best equals the maximum of the best and my current accumulation. Then we'll print that best. So what I did here is I'm checking if my current accumulation is better than what I have as my best accumulation, then I set my best accumulation to my current one. And at the very end, after we try every subarray, we print that out at the very, very end. Any questions on this one? Anything that's not clear, let me know. Let's code it. Oh, it's all here, never mind. That's so oops. Okay, what's this one in Python? First thing we're given is we're given the length of this array. So how about we get the length? I just need to move this computer over here because I can't see where I'm typing. So how about we call this one length equals int of input. This will get a single line of input and convert it into an int. You guys ready for some black magic? That makes sense, right? I'll show you what this thing does. This is a very tough one. So first it calls input, which gets a line of input. In this case, maybe our line of input is this. Maybe our line is this. Then we split it. So we split this up into an array, but each of these are strings. So before we are able to treat them as numbers, we have to map each of those to an integer, which is what this map does. After that, we have to turn it into a list. Map doesn't return a list. It actually returns a map generator object. I'm not actually sure how that works, but when you use map, usually you start it with a list, so you can use it as an actual list. Other languages, of course, may have different ways of doing this. If you can either Google that one. For C++, it's CIN usually to get the standard input. For Java, there's a few ways. Usually you want to use the buffered reader or the scanner, something like that. But that's how we do it in Python. Differ by language. You can look up how your own language does it. How this one is going to work now, let's do the best equals 0, accumulation equals 0, and parity equals 0. I'm going to do that. For every number in that array, we're going to say new parity is equal to in modulo 2. We're going to say if parity equals the new parity, what we're going to do is accumulation plus equals our current number in. In the else case, we're going to switch the parity. We're going to set the accumulation. And then, of course, we have to do the best equals the maximum of the current best and our current accumulation. At the very end, let's print out the best, and let's see what happens. Does this one work? There we go. Nice. Cool. First one done. Does that one make sense to everyone? Does anyone have any questions on this one? Let me know if you have any questions. Of course, let me know if you want to stop, and I'll go back. N-bonacci. This one is a bit of a tricky one. How N-bonacci works is that the Fibonacci sequence is generated by taking the sum of the previous two elements. N-bonacci will be taking the sum of the previous N elements. Maybe if I have the 3 Bonacci sequence is where the next term is generated by taking the sum of the previous 3 elements. So in this case, if I have the 5 Bonacci sequence, let's get rid of this one. If I have the 5 Bonacci sequence, it goes like this. And in this problem, I have to say, I'm saying that the starting point is n minus 1 zeros. So if I have a 5 Bonacci sequence, I have 4 zeros. If I have 2 Bonacci sequence, I have 1 0. If I have a 10 Bonacci, I have 9 zeros, followed by a single 1. So if I have the 5 Bonacci sequence, I will have something that looks like this. And then I generate the next elements of the sequence using this list. So my next element for this one would be the sum of the previous 5 elements, because we're on a 5 Bonacci. 0 plus 0 plus 0 plus 0 plus 1 is 1. The next element would be 0 plus 0 plus 0 plus 1 plus 1. We're not including this 0 because it's not part of the previous 5 elements, would be 2. The next one would be 0 plus 0 plus 1 plus 1 plus 2, which is 4. Then 8. Then, what is that, 12, 14, 15, 16. Then 1 plus 2 plus 4 plus 8, then 31, so on and so forth. So how would we generate this 5 Bonacci sequence? Let's start with how would we generate the 2 Bonacci sequence, the regular Fibonacci sequence. Maybe we have an array of, oops, wow, what happened here? We have an array of 0 and 1. Maybe every time we add a new element, we want to do the sum of the previous 2 elements. So maybe we want to do ARR equals this. ARR dot append. This is how you add an array in Python. To get the previous 2 elements, you can either do ARR dot, sorry, let's do the length minus 1, sorry, like that, plus ARR len of ARR minus 2. In Python, there's a little shorthand for it where you can do ARR at minus 1 plus ARR at minus 2. As you do a 2 Bonacci sequence, the tricky part is that we have to do N-bonacci. So the number of parameters in here might vary. I might give you 100 elements to take some of. So this will be a bit tricky. With this one, we're going to need a double for loop to do this one. But the constraints are small enough so it shouldn't matter. I think there is a way to do this one with a prefix sum to make it faster. I haven't tried that way. If anyone can do it, let me know. So we're gonna do it like this. We're given a starting point. So we're given a 2 Bonacci sequence. We have to find the index of 21. Given a 4 Bonacci sequence, find the element of 21. It doesn't exist. And given a 48 Bonacci sequence, we're trying to find this behemoth at index 97. Apparently, I don't know. I didn't actually do this by hand. I don't want to do that by hand. I make a computer do it. So let's do it like this. To generate, let's say, a 4 Bonacci sequence, we're going to start an array with some number of zeros. Plus a 1. We're going to create the sequence until our last element or our current element is greater than or equal to the number we're looking for. Because if we go over, there's no point in going over because we're looking for if the element occurs. So we're not going to go over. We're going to stop when we go over. So we're going to keep generating. And how about we call our target is the number we're looking for. Let's say our 21 or something. With that, we're going to say, while the last element in my array is smaller than, let's do it like this. Smaller than the target, we're going to make a sum equals 0. And then we're going to do a for loop going backwards. So for, let's say we're given like a in is our N-bonacci sequence. In this case, maybe it's 4. For I in range, we're going to start at the last element in the array. So we're going to start at length of the array -1. We're going to go down to length of the array -1 minus the in. Do you see where this in comes from? Because the in is the Fibonacci sequence, like that, or whatever sequence we have. And we have to go down to that amount. We're going to loop backwards. So we're going to put -1 as our increment. I don't actually know if this math works out. Maybe it's a -2, but maybe if I have like a 0, 0, 0, 0, 1, we want to put in a next element. Length is 5, so we start at here. We have to go down to length is 5 -4, -4, 1, 2, 3, 4. It actually should be a -2, I think. But you can think about the math later. But all it does is looping down these in number of times. We're going to do sum plus or equals array at I. And then we're going to append that sum to our array. Array dot append sum. But also, if our sum equals the target, we need to print out, we have to print out the, I think the index of where the element occurs. First occurrence of a value in this one. In this case, that 221 should give us 8. As an example, we'll do the Fibonacci sequence from 0 to 21. It goes like 0, 1, 1, 2, 3, 5, 8, 13, 21. We do that because 0, 1, 2, 3, 4, 5, 6, 7, 8. 21 occurs at index 8. So we're going to print out, because the length of this one is 9, which is always 1 more than the index where it occurs. We're going to print out the length of the array -1. And then we're going to exit. We're just going to completely stop the program. But if this loop ever goes out of range, which means that we didn't find it, and we go over the target, we're going to print -1, which means it doesn't exist. And that's just what the problem says, because it prints out -1 if it doesn't exist. Does that make sense to everyone? Any questions?
I think like when you said the prefix thing, you can, instead of adding like n, like you can save time by doing like your previous element plus your previous element minus like the n before. That.
Maybe.
And then because like you're already adding it, you have that like, and then you add your new index and you push it.
That's true. That could be cool. Yeah.
One instead of like that.
Right. So you can think about a few more optimized ways to do this one. As Rena said, you could keep like the past 5 elements in an array or a sum and just add that one every time. But this was a bit of a naive solution. It works, it passes. but there are faster ways. But this is just like the simplest way to do it. Everyone's, of course, welcome to think of that. I hope everyone does. Let's start by getting these two elements. Let's do in target equals. I'll read in this line at once, and I'm gonna get their ints. So map int input dot split once again. And we're gonna do it like this. Array equals 0 times in minus 1 plus 1. Just so we can see what it is, let's print out the array. Obviously this one's gonna fail, but I just wanna show everyone what the array looks like. That's our starting points. 3 zeros, 1, 1, because we have a 4 Bonacci. 1 0 and 1 1 because we have a 2 Bonacci. 47 zeros and 1 1 because we have a 48 Bonacci. So after that one, let's do that while loop. While array at minus 1, the very last element in the array is smaller than the target. We're going to do that sum equals 0. We're going to do the for loop for I in range of len of array minus 1, len of array minus 2 minus in, negative 1, we're going to go downwards, sum plus or equals the array at I. And then we're going to say array.append sum. We're going to say if that sum equals the target, we're going to print out the sum and immediately exit the program. But if we don't find it, if we go over the target, if we go after the target, we're going to print out a negative 1 instead. Did I make any math mistakes here? I did. That's not good. What's going on here? How about we print out the sum every time? What's going on here? 2, 3, 6. Let's print out the array. Sure, sounds good. Thanks for being here. Let's change the math a little bit. Apparently that's a minus 1. There we go. And instead of the sum, sorry, I made that one wrong. Let's do length of the array minus 1. So like that. So I did make a little math error there. Math is not my strong suit. I will say for this problem, if you're doing this one in a language with data types, Python is like you can have very, very big integer, a very arbitrarily long integer. If you're doing this one in Java, C++, you will want to use the 64-bit integer. In Java, that's just long. C++, long will give you a 64-bit. Python is silly like this, so I can it automatically handles that. But if you're in a language like that, then you have to use a 64-bit integer because we have a number that's up to 10 to the 18th. That 10 to the 18th does not fit in a 32-bit integer, which has a limit of around 2 billion. But the 64-bit has 9 times 10 to the 18th as its limit. So be careful of that. Let's take a look at trinomial. That's an interesting one. We want to find a pair of terms that, when multiplied, get this trinomial at the very top. We're given b and c, and we're also given a. The term for x squared is 1. Trinomial b will have that a equals something other than 1. But for this one, our b and c are some kind of values. Our a is 1, but b and c are not 0. So for this one, 1 and 6, let's see what that one looks like. If we have, don't look at this code. If we have a -1, -6 is our input, that means our b is -1, our c is -6, which makes our trinomial look like x squared minus 1x minus 6, or just x squared minus x minus 6. Is everyone familiar how to factor trinomials like this? Usually that one's taught in math, but what we're going to do is we're going to try every possible. Okay, let me explain how to do it first. We need to find two numbers. Let's call them x and y, I don't know, or what do I call them inside the statement actually? S1, S2 maybe? S1 and S2. I don't know what the mathematicians call these terms. Is there any fancy word for this? For this one? We're trying to find these two numbers, the -3 and the +2. Is there any math word for these numbers inside the binomials?
Addings and subtractions.
Okay, we'll call them add-ins for now, subtractants. So we're trying to find those two numbers. And how this one works, if we multiply x minus 3 and x plus 2, x plus 3 times x minus 2, I did that one wrong actually, it should be x minus 3 and x plus 2. If we multiply that one out, using this square, that would end up being x minus 3, x plus 2. That one would be x squared. We're multiplying x and x and 2 would be 2x. X minus 3 would be negative 3x. And 2 times negative 3 would be negative 6. Summing all those together would end up being x squared minus 3x plus 2x minus 6, or x squared minus x minus 6. So pretty much we have to find these two numbers, minus 3 and 2. So they multiply to negative 6, our c, and add to negative 1, our x. What is going on here? Did this one break? Oh, it turned off. Why?
You know, we've had problems with these overheating.
Oh, okay.
So we have had it on for a while.
I see, okay. Okay, hopefully it doesn't explode. So like that, we have to find S1 and S2 that multiply to C and add up to B. And we can do that with just some brute force. We can try every possible factors of C, but the problem is coming with the negative symbol, because if it's negative, then we'll have to do a little bit of tricky stuff to do that one. But let me show you first the code for finding all of the factors of a number. I'm going to call this one define factor of a number. We're going to say, I'm going to start off in I equals, let's do like this actually. I equals 1. And we're going to do factors equals an empty list. And we're going to just add onto that list our possible factors, our factor pairs. All good? Sure, sounds good. Thank you. I'm going to do a while loop. While.
We're just going to head out, so we're saying bye.
Sure, sounds good. Thanks for your help.
Thank you for everything.
For sure.
Thank you so much.
Thanks for your help. That was good. We're going to do a while loop. I'm going to say while I times I is less than or equal to in. And I'll show you why this is later. But let's do like that for now. We're going to say if that in modulus I is equal to 0. How this one works is we kind of did modulo before with the odd and even numbers. We're going to say, since modulo gives us the remainder of in divided by I. If the remainder is 0, then it means it is a factor, because there's nothing left over when you divide it. So if that one works, we're going to get two factors, which is going to be S1 might be our I, S2 might be our in divided by I. I'm using this double slash because it's integer division. In Python, that's how you do integer division. In other languages, maybe it is some separate thing. Usually it's just one divide. But we're going to append to our factors our S1 and S2 as a pair. In Python, that's called a tuple. In other languages, you can use an array or some kind of built-in pair data structure. And I plus equals 1 at the very end. Let's write this one down, and then we're going to see this one in action. So I want to do my I equals 0. Factors is a list. While I times I is less than or equal to in. If, it should be a 1, actually we don't want to divide by 0. If in modulo the I equals 0, if there's no remainder left over, we're gonna do S1 equals I maybe, S2 equals N divided by I. We're gonna do factors dot append S1, S2, and I plus equals 1 regardless. We're gonna return that factors. How about we just give this one a try? How about I do a print factors of like a, I don't know, what's a good one, 12 maybe? Maybe I'll do like a 25, maybe like a -6. Oh, that's unfortunate. What's going on here? Wow. Ignore this one for now. That's my custom checker. But I have to do a problem with append. I have to make a tuple, pair of elements. Let's see. 1 and 12. 1 times 12 equals 12. 2 times 6 equals 12. 3 times 4 equals 12, right? That makes sense. 1 times 25 is 25. 5 times 5. The reason I do this I times I is less than or equal to N is because I don't want to go over like a, if I'm calculating 25, I want to do 1 and 25, then 5 and 5. I don't want to do 25 and 1 because we've already done 1 and 5. It's not going to have an effect on the code on the program, but it'll just make it run longer. So this is a little bit optimization. The complexity for factor would be O of square root of N. So if you have like, if your number is 10 to the 10th, it'll run up to 10 to the 5th operations. That's a problem. What's going on here? There's no factors for -6. Anyone know why? When N is negative, I times this N is always less than I times I. How about we change it to an absolute value of N? And run it like that. 1 -6, 2 -3. But how about we also try -1 6 and -2 3? Those are also possible factors. If I give you a, like for this one, if I do a 6, we can do x plus 2 times x minus 3 would be x squared minus x minus 6. But if I do an x squared plus x minus 6, this one would not work because -3 and 2 would add up to be -1 instead of +1. How about we append onto here as well, in addition to the positives, the inverse of both of them? Because these two still multiply to the number. Because 2 negatives times negative is always a positive. And look at that, we have negatives for all of those. We have a 2 -3 and a -2 3. Now to actually put this one into the function to actually find the stuff, let's start by getting that input. How about my BC equals map int input split. I'm not using list here because we're immediately putting it into values. I don't need the list. We're going to do like this. We're going to factor C, and we're going to go through every pair of factors and see if they add up to B. Let's do it like this. C facts equals. And then we're going to see for that S1, S2 in C facts. We're going to say if S1 plus S2 equals B, then we're going to print out S1, print out S2. That's what it wants. And we're going to completely break. Does that make sense to everyone? We're just trying every possible pair of factors. We're just going to choose one that works. Wow, it's taking a long time. Why? Oh, that was weird. I'm actually going to copy paste the code for this one because there's a lot of repeated code in between. Where did my code go? There's a lot of repeated code between Trinomial B and Trinomial A. Only one for this one is that our A is not necessarily 1. Our A could be 2, or it could be 2 again, or 12 maybe. This one gets tricky. I'm I'm gonna change here actually an A, B, C. And then let's think about this one a little bit more. Let's go through the function maybe 2, 5, negative 3. Go through that example. In this case, maybe we have a 2x squared plus 5x minus 3. Is that what I had? Yeah, 2, 5, negative 3. So we need to find 4 numbers for this one. S1, S2, which is the second thing to the thing. So Tx plus S is our format pretty much. We'd find 2 of these ones that work, maybe for a T1, S1 and a T2, S2. So how about we do it like this? We make another grid, and we're going to see how can we get this one, or ax squared plus bx plus c. We have to just do this 2x squared. In this case, the answer could be maybe 2x 3 for a 6x, x times 2x for a 2x squared, x times negative 1 for a negative x, and negative 1 times 3 for a negative 3, for a final answer of 2x squared plus 5x minus 3. The tricky part is actually getting that one, because we have to find... The tricky part is that we have 3 and negative 1, which have to multiply to negative 3, or c. But we also have 2 numbers here, t1 and t2, that have to multiply to a. So we're finding a bunch of pairs of factors for that one. 2 different pairs of factors. One that adds up to a and one that adds up to c. So same logic as before, we can brute force by finding all the factors of a and all the factors of c, and then testing to see if multiplied together, they get to b. The logic for multiplying is, if we call this one, let's do it like this, T1, S1, T2x, S2. This one would end up being T1, T2x squared, T1, S2x, T2, S1x, and then S1, S2. At the very end, our equation has to be A has to equal T1, T2, B has to equal T1, S2 plus T2, S1. C has to equal S1, S2. We're just going to brute force every possible way to get B, because we can get the factors T1 and T2. How do I undo this one or redo? Oh, my code is disappearing. S1, S2. Just like before, we're going to brute force through all the factors of here, see if they equal to B. Let's do it like this. ABC, A factors for T1 and T2 in A factors, and our output format is going to look like this. We have to print out T1, S1, and then T2, S2. And we're going to do it like this. If T1, S2, so T1 times S2 plus T2 times S1 equals B. We print out those. And let's see. Well, that's unfortunate. What's going on here? We're not printing out anything. So there is a tricky one for this one, in that there is a case where we could swap them around. So there's the other case of we can do T1 times S1 plus T2 times S2. Well, that was unfortunate. Cool. The reason why this one has to be there is because I can either do T1x times S1, but I could also swap these around for S2, S1, and S2 like that. Make sense? Math is a little bit weird, will not lie. We're just going to try every possible combination, see if it works. Next one, tour guide A. Tour guide A was harder than tour guide B, I guess. This one is actually a interesting problem. How did the people who attempted this one solve it? I'm curious. Brute force? Maybe brute force? Try every possible starting time? Did anyone try to sort it? No sorting? Let's do it like this. I'm going to draw it out first, and then we're going to see how this one works. I'm just going to give some sample test case like this. Maybe one interval like this. That's one student. Our second student could be like that. Our third student could be like that. Our fourth student could be like this. If we just think of this one as the timeline, you can see here like this. One student is entering. So like at this point, we have 0 students, right? At this point, we have 1 student. At this point, we have 2 students. At this point, we have 1 student. At this point, we have 2 students. At this point, we have 3. Did I do my math right? I did not. This one I have 2. Okay, let me make this one a little bit more clear. Like that. For this small section in here, we have 2. In this section, we have 3. In this section, we have 2 again, then 1, and then 0 onwards. Every time a student enters, we can have a counter that goes up by 1. Every time a student exits, we can have a counter decrease by 1. And we just want to find what's the maximum of the counter. How that works, we have to split up each interval into the start and the end. Maybe we can assign the starts to a 1, because every time we see a start, we increase the counter by 1. Maybe we see an end, we decrease the counter by 1. And then we're just going to we'll sort it, sorting all the starts together, because we're going to look at this first, then this, then this. So the order is not going to be determined by the starts and the ends, pretty much. We're just going to go in this order. That's terrible. Does that make sense to everyone? So let's do it like this. We're going to use pairs once again, the tuples, or maybe an array in other languages. So we're going to do, we have to first split up each interval in where each interval is a time, like a H, H, M, M, S, S, and then a space, and then another H, H, M, M, S, S. We have to split it up on the space to split into 2 intervals. The first H, H, M, M, S, S will get a 1. The second one will get a 2, or sorry, a negative 1, because we're decreasing the counter. If we see 1, we're going to increase, negative 1, we're going to decrease. So let's do it like this. I'm going to first start by getting the number of students. Then we're going to get the actual students themselves. We're going to do 4. I'm going to do actually intervals. 4I in range in. We're going to do start end equals input dot split. In this case, I'm not using int because these are not integers. For the people who did this problem, did anyone try to convert this one into seconds first? Yeah? You don't actually need to. It's very good practice to convert it to a same unit. But for this one, the string comparisons work out, so you don't actually need to. But it is a good practice to do that. Other way works for this one. I'm not going to, just because string's funny and I'm lazy. So I'm just too tired lazy. But if you want to convert it, you can either convert it to, and then if you need to print it out afterwards, you just convert it back. So start end equals intervals dot split. We're going to do intervals dot append. We're going to add to this one start comma 1 and an end comma negative 1, because at the start we're at getting 1 student, and we're ending, we're subtracting 1 student. Thankfully, to make it easier, I set it to there will be no intervals that are overlapping, so they're all going to be unique. very end of this one, let's do a sort of intervals. And then let's see what happens when we print that out. Well, that's unfortunate. Is there no way to sort? Let's do like this. So first, get that 8 o'clock, we're getting 1 student. At 9:50, we're getting 1 student. At 10:50, we're getting 1 student. At 10:10, we're losing a student. That student is going home. Same with 14:30, which is over here. Same with 15:00:10 over here. Pretty much so on and so forth. What we're going to do now is I'm going to have to find the first time that has the maximum number of students. So 2 things I have to find. The maximum number of students at once and the time where that occurs. What we're going to do here is best time equals to something, I don't know. And then we're going to do best count equals 0. And my current count equals 0. Then we're just going to go through every student's for time, comma, increase in intervals. And we're going to do like this. If we're going to do cur count plus or equals, or plus equals the increase. We're increasing the cur count by whatever's inside increase. Increase is a positive, which means I get 1 student. Cur count is going to go up by 1. But if my increase is negative, which means we're losing a student, cur count is going to go down by 1. We're also going to do if my cur count is bigger than my current best, we need to set the best time to that current time. And we have to set the cur count, the best count to the cur count. Does that make sense? Any questions on this one? It's a bit of tricky logic, right? It's going to fail because I'm printing these ones, but see how this one matches. Do that. Let's see those points. Any questions on this one? Is anything confusing? For guide B, I'm going to copy the code here actually, at least for the intervals. Tour guide B is a tougher one. I'm surprised more people got B than A, at least as in percentage-wise. 60% of people succeed on this one, but this one uses a technique called greedy interval scheduling. UC Davis people might already know this one from a funny course, that algorithms course, very goofy course. Yeah, fair enough. How greedy interval scheduling works is that we're going to first start by sorting the intervals. We're going to keep the intervals all together. We're not going to split them up this time. But we're going to sort it by end time. So let's take this example again of 9:50, 14:30. I'm not going to remember any of that. So let's just do this one. Greedy interval scheduling. Oh, okay. Let me explain the problem first. The problem is that we have to find the tour guide is now giving one-on-one tours. So we're going to do 1 student at a time, and we're trying to figure out what's the maximum students I can give a tour to in a day. The tour guide's final exams are over, so the tour guide has more time on his hands, so we can actually give the tours now. How greedy interval scheduling works, and I'm actually going to make a better example like this. This, and this. From this, can someone tell me the maximum amount of tours I can give in a day just by looking at these pictures? If this one is the start, and this one is the end of a single tour. 3, right? So we see that 3, which is this one. And then we're gonna not do this one. We're actually gonna do this one next. And then we're going to do this one. That's gonna give us 3. I don't think there's any other combination that gives us 3. The other ones will give us 2. or are invalid. How greedy interval scheduling works is that we're going to sort this one by end time. So the first end time first, we're going to look at this one first. We're going to look at this one second. We're going to look at this one third, because this one has a shorter end time than this 4. And this 5. Oh, I can't erase that. So the shortest end time goes first in this order. How this is going to work is that we're going to select the next element that is compatible with our current elements. Compatible means that it doesn't overlap with any ones in my current ones. Let's say I select the first one. The first one that is compatible is our elements 3, because its start is greater than my current end. Does that make sense to everyone? Next one is going to be this 5. My current end would be this one. And 4 is not compatible with 3, right? This one is 3, this one's 4. Because its start is not greater than this end. So we're going to pick 5. Because the start is greater than this end. That's going to be our intervals. The first step is to sort by end time. And then we're going to go through our intervals. And we're going to do pick interval that is compatible. So let's do it like this. We're going to first start by, not like this actually, we're going to do intervals.append start comma end. No sorting this time. Print it, sure, that's fine. I'm going to do this one just to make sure it's a pair. I don't want to keep the space there. But basically it's just a sort and an end. We are actually going to sort this one. I forgot, but this one does have sorting in it. I'm having a bro moment. But we're going to sort it by the end elements. Every language has its own way of sorting it. But in Python, the way to sort is using the key equals lambda pair. We're going to sort it by the second elements, index 1. This depends on the language, of course, but in Python, all this means is that I'm sorting it for each pair. I'm sorting it by the second element inside the pair. So now let's print it out. This is before sorting and after sorting. Before sorting, it's all of this stuff. Let me zoom out a little bit. How much do I have to zoom out? There we go. But after sorting, we can see that we're all ordered in the end time. So we're all going in increasing end time. 10, 14, 15, 18, and 19. So now, we're just going to keep selecting until we run out of stuff. So let's give that one a try. I'll get rid of this stuff. We don't need this one anymore, the prints. Printervals. Let's do 4, start, and in intervals. This one, our best, sorry, my num students equals 0. I start with 0 students. Then I'm going to go through here. If my start is bigger than my current end, we have to set, because if we remember back here, if we pick this one over here, then we have to set the new ending point to the ending points of this interval that we just chose. So my cur end will become, what do we call this one? End. My num students. How about we just do a print num students? How about we make our cur end start off as Let's see. Oh, it's taking a long time. Come on. It's a bit of a tricky one, this greedy interval scheduling. But does the way of doing it here make sense to everyone? Now you know this. As another tool for your repertoire, for your arsenal. Algorithms class will be very easy for all of you, now that you know this. What's next? Triple fourth. This is the problem of all time. Maybe some people have seen my my funny solution, where it's a 5-liner. Let's see, where's the 5-liner? Yeah. I don't know how it works, I just know that it does work. Some people tried to brute force this one, which is fine. This one does work with brute force. But let's do it like this. I'm going to write a function to solve this one, and then we'll try to make it better. Triple fourth. Let's try this one again. I'm just going to get to coding this one, but we'll go through this one first. So if we start at a value of 3, every time I press the button, the counter is going to decrease. But on every third time I press it, the counter is going to go up by 1, which actually means it stays the same because I'm decreasing and then increasing, so it stays the same. Every fourth time I press it, the counter is going to increase by 2, which really means it increases by 1 because it goes subtracts 1 and then plus 1. Every 12th count, it increases by 3. It's really by increase by 2. So on the first press, I go down to 2. Second press, I go down to 1. Third press, I decrease, then increase, so it stays the same. Fourth press, I decrease to go to 0, and then a plus 2 for 2. Fifth, I decrease to 1. Sixth, I decrease, increase. And seventh, I get to 0. We want to see how many moves does it take until I cannot press the counter anymore, where it goes to 0. I'm just going to get to coding this one. It's a bit more of an implementation one. But I'm going to write a function to brute force this one, and then we'll see if we can do better. So I'm going to call this one for... I'm going to call this one like that. My current number equals int of input. So every time I call STA, I'm executing one single query. And then I'm going to do for range of int input print STA. So we're going to do it like this. For while n is greater than 0, my current move starts at 0. We're going to do current move plus equals 1 and n minus equals 1. Every third turn, we increase it by 1. So we're going to say, to get every third turn, 3, 6, 9, 12, 15, our current move has to be divisible by 3. That's another modulo 1. If current move modulo 3 is 0, n increases 1. If it's divisible by 4, increases by 2. And print my current move. Right? That makes sense? Let's do something like this. How about we print out every possible move, starting from 1 to, let's say, 10. I'm going to refactor this one a little bit, so I give the input as I call this one. For I in range of 1 all the way to 10, I'm going to do print I and the number of moves. Like that. Obviously going to fail, but it's going to go like this. 1 goes to 1, 2 goes to 2, 3 goes to 7, 4 goes to 11, 5 goes to 19. But what if we took a look at this one and tried to find a pattern? Every even one, every odd one, it seems to increase by 12. See that? Starting at 7, it increases by 12. Every odd one will go. Same with every even one. but it starts at 11. So how that one's going to work is there a way to copy paste this one? I'm not sure. I'll just move this one over here. I'll do this one. I'll move it back later. How's it going to go? 1 to 1, 2 to 2. And then we're going to do, these ones are one case, 3, 5, 7, 9, 11, so on and so forth. 4, 6, 8, 10, 12. 3 is going to go to 7. It's going to go to 19. 7 is going to go to 31, 43, 55. 4 is going to go to 11. It's going to go to 23, 35, 47, 59, something like that. And from this one, we can just kind of like make an equation for it. We can say like, if it's odd, we're going to print out some kind of way to map a 3 to 7, 5 to 19. An equation that you could use is subtract 3 first. Maybe if my in is like that, you can go to in minus 3 times 12 plus 7. So maybe if my in is 9, I can do 9 minus 3, which is 6, times 12, which is 72. That's not right. Oops, hang on. My math is not right here. Is it right? I'm going to do times 6 because, okay, let's do like this actually. Plus 7 divided by 2 and then times 12. So 5 minus 3 is 2, divided by 2, that's 1. 1 times 12 is 12, plus 7 is 19. 9 minus 3 is 6, divided by 2 is 3. 3 times 12 is 36, plus 9 is 43. We can do something similar for this one, maybe a in minus 4, divided by 2, plus 11 for this one. This is kind of just like print out the stuff and then try to find a pattern, pretty much. It's a pretty interesting problem. So we're going to take these two equations and put them into the code, just like this. I'm going to make this one better. Instead of doing this code like this, there are 3 cases. If my in is less than 3, return in. Because that 1 goes to 1, 2 goes to 2. Those don't have anything special. If my in is odd, I have to return a in minus 3 divided by 2 times 12 plus 7, was it? But if it's even, for in minus 4 divided by 2 plus 11. Let's go to the stuff here and see the quick solution. There are some other ways to solve this one, of course, besides just looking at the possible answers, trying to find the pattern. But there's a few brute force solutions you can look at. I'm not familiar with those methods. I just solved it this way. But there are some ones that I can post later as examples. So I'll post that one later. But I'm not familiar with those ones. My favorite problems, the hard ones. Let's see. Fields of flowers A. I put in a joke here because computer scientists don't like grass. So we're trying to take pictures of flowers, but we don't want our picture to have any grass in it because grass is scary. We were originally gonna, as another computer scientist joke, we were gonna put deodorant as a prize here, but unfortunately we weren't able. So next SCPE, spring 2025, we'll have deodorant as a prize, just as a joke. This is gonna go like this. We're given our length of the array and the maximum size of our picture. And we have to find the maximum number of unique flowers, elements in this array, that we can get a picture of with a maximum picture size that we're given, 3. In this case, our 2 pictures we can take are 1, 1, or a 2. We can't take this picture because it has grass in it, but we can take this picture, just this one, or just this one as well. For this one, our solution is 2 because our maximum picture, we can take this one for 2 unique flowers. And for the 7 and 4, we can either take this picture for 4 or this picture for 4. This one is a sliding window problem. Anyone heard of that technique before? It's a pretty popular one. SCPE 3 definitely will have sliding window. Take a listen. Very cool technique. And it's going to go like this. Let's go through that one of 1, 1, 0, 2, 1 with a window size of 3. What we're going to do is we're going to maintain a counter of left equals 0. That's our starting point. And then we're going to go through this array. And for every element that we go here, we're going to add it to our set of flowers. And by set, I really mean a lookup table of flower ID to how many flowers it occurs. For that one, we're going to use the dictionary or map in other languages maybe. You got your hash map, your tree maps. Flowers equals that. If anyone is unfamiliar with map, all it is a key value pair. What this map is going to hold is the amount of flowers, flower ID mapping to how many times I've seen that flower inside this range. So we're going to do it like this. We're going to keep moving forward in here. We're going to maintain 2 pointers, our left and our right. When I go to 1, like that, it's not grass obviously, so I can continue. But every time I go to 1, I add it to my flowers. And then I'm going to move it forward. This one, I add it to my flowers. Okay, in this case, my flowers equals 1 has 1. This one, my 1 has 2. Grass, what if I see grass? I need to clear my flowers because I don't want any grass in it, because programmers are afraid of grass. So my map is clear here. When I get to this 2, I'm going to set this one into a 2 has 1, and a 2 has 1, and a 1 has 1. At the very end, we have to find the maximum size of our flowers dictionary. The size of this one is 1 because there's only one element here. One element here is 1, and then 1, and a 2. Are you heading out? Sounds good. See you later. Thanks for joining us today. So we're going to find the maximum size of the dictionary. But of course, we have this window size constraint as well, so we have to figure out a way to remove things from the dictionary. If I have a thing like 3, 3, 1, 2, 4, 5, like that, and our width is 4, I can look at this one first. So at this point, our dictionary is going to contain 3 has 2, 1 has 1, and 2 has 1. If we move this one to the right, I still have, so when I move to the right at this 4, I have to, since this now has a length of 5, so I have to shift this left pointer to the right one by removing this 3 from the dictionary. I can do that by subtracting 1 from this 3 elements. So this window would have 3 to 1, 1 to 1, 2 to 1, and 4 to 1, like that. So this one has 3 unique, this one has 4 unique. Same as when I move to this 5, I add a 5 to the dictionary, so it goes 3, 1, 1, 1, 2, 1, 4, 1, and 5, 1. But then when I move this one over, I remove 3 from the dictionary, so this goes to 0. Because it's 0, I'm also going to remove it completely from the dictionary. So the dictionary size will be 4 in this case. Pretty interesting. Let's get to code this one. So our left pointer is like that. We'll go through logic as I coded this one. I'm going to get my length size equals map int array is list map int input dot split. And then we're going to say my left equals 0. My flowers is going to be my map, like that. What else do we need? My best equals 0. And we're going to go like this. We're going to have my right pointer, and that's going to keep moving forward. And we're going to say, if my array at right is grass, then I want to completely remove all of my flowers and start over my L at 1 more than right. So I'm going to do L, so we're going to do flowers equals a new dictionary, clear it out completely. L equals right plus 1. I have to do right +1 because I want to skip over that one. If I'm at a grass right now, I have to go past that grass for my left pointer because my next window cannot contain grass at all. In the other case, we can say if right minus left, so my size of this one, I'm actually going to have to do r minus l plus 1 because r and l are inclusive of the bounds. So maybe if I have an example of 1, 2, 4, 8, 16, my r and my r here, ln r, we have to find is this, and maybe my length, my window maximum picture size is 3. Sorry, let's do a 2. In this case, r minus l is 2, right? Because this is a 0, 1, 2, 3, 4, 5. If we look at the indexes, 3 minus 1 is 2. But it's actually going to be 3 minus 1 plus 1 because these are both inclusive. If it was 4 minus 1 or 3 minus 0, it would be fine. But since 3 and 1 are both inclusive indexes, then we have to do plus 1 at the end. If you do inclusive and exclusive, you don't need to do that plus 1. But there's a bit of math that works out there. So I need to do that plus 1 here. You can try it for yourself, of course, when you code this one. If that one is bigger than the size, I need to do flowers at L minus equals 1. I'm going to remove one flower from the left bound. I'm also going to say if that L is equal to 0, we're going to delete it. There we go. And then we're going to do flowers. And we have to actually add our right flower to the array. We say rf equals flowers, array at r. We're going to say if our dictionary already contains rf, we're just going to add 1 to that. But if it does not contain it, flowers at rf equals 1. And of course, our best equals the maximum of our best and the size of our flowers dictionary. Let's see, did I mess up on this one? That's unfortunate. What's going on here? That was L minus equals 1. Because I forgot to do left flower equals array at L. Flowers at left flower. Like that. Okay, progress, I guess. Why is this still not working? Oh, there it goes. Okay. Should we give it time for rest while I figure this out? Let's see. Flowers at L, LF minus equals 1, flowers at L. Let's see. Let's wait for it to keep on going. There it is. L equals R plus 1. Right, R equals that. And we're going to do a continue. Because we don't want to keep this grass kind of thing. So we're just going to skip the rest of the current iteration. So when we touch a grass, we're not going to do any of this. That's why we avoid grass, people. Grass is yucky. It makes our code not work. That's unfortunate. What's going on here? Runtime error. If only it shows me what that runtime error is. All right, let's try again. LF minus equals 1. Does anyone know what I'm doing wrong? Because I sure don't. What does everyone think? Anyone see anyone weird? Anything weird? Could it be something that's going out of bounds, maybe?
Use a map or set?
This one's a map.
Could you set?
Nah, set wouldn't work. We also have to keep track of how many flowers we've seen as well. Because we have to count that one. Okay, could be. If this range is bigger than my size, then I'm going to do my LF equals that. Flowers of LF minus equals 1. I don't know. Let's see. Maybe like LF nuts in flowers. I don't know. Huh. I'm stumped. I don't know. Maybe I'm able to see this one. Runtime error. Nope, even when I made this contest, I'm not able to see it. Let's see what I did before. Maybe I had a better idea when I was fresh. Like this. Current flower is like this. If it's inside the window, we're going to increase that one. Else it's 1. Could it be moving this one up here? Maybe what's happening before was the edge case of my window only having 1 element in it. Making something wrong, but it's still going wrong here. Let's see, what else did I do that could be giving an error? If it's bigger than the image size, we're going to decrease that one. It goes to 0. Oh, that's why I have to do a... Oops, let's do that one again. L plus equals 1, because I have to actually shift the window right, which I forgot to do. So, let's give that a try again. Okay, there we go. Setting window is a tricky one. So, take this one at home, hopefully. Give this one a try. There are a few edge cases on this one, as you can see by my stumbling through it. Fields of Flowers B goes on the same concept of the flowers in the fields, but we have to find the ways to go through the fields without stepping on the flowers. We have to face our fears and touch the grass, unfortunately, for this one. Thankfully, we have shoes, so we're not like stepping on the grass directly, but we will end up having to touch grass regardless. How this one works is that we can move. We have 3 movement options. We can either go to the next step, hop to 2 steps from now, or jump from 4 steps from now. Whoa, look at my chicken. So how this is going to go is that we're given a list. A 0 represents grass, 1 represents flower. We have to find all the ways to get from this 0 to this 0, all the way from the start to the end, without stepping on any flowers. In the first case, there are 4 possible sequence of moves. You can start at this 0, walk to this 0, hop to this 0, walk to here, or walk to here. Or you can walk to here, hop, then a hop to this one. Or you can walk and jump all the way to here by jumping 4 spaces, or jump all the way to here and then walk 1. That makes sense? So we're finding how many possible steps there are. This one is dynamic programming, my favorite topic, besides BFS, of course. SCPE 3 will have BFS. How this one works is that if we start on, and I'm just going to copy it on this input, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 2, 3, 4, 5. If I start at here, if I have a function called f of 0, I have 3 choices to make. I can call f of 1, f of 2, or f of 4. Every function call means starting at this point, how many ways are there going to be to get to the end? So f of 0 is that starting at this point, the number of ways that to get to the end is the sum of the number of ways to get to the end starting at here, the number of ways to get to the end starting at here, and the number of ways getting to the end starting at here. Does that make sense to everyone, at least conceptually? Because, yeah, at that point, the three choices I can make are go forward 1, 2, or 4, and the number of choices, or the possible number of steps, is the sum of all those 4 choices. So f of 0 is going to be f of 1 plus f of 2 plus f of 4. And of course, these ones can make their own choices. F of 2, f of 3, f of 5, f of 3, f of 4. This is going to get messy real quick. Oh, this is terrible. F of 8. So let's make it less messy. See how there's a lot of repeating in here? F of 2 is called how many times? Twice. F of 3 is called a bunch of times as well. F of 5 is called a bunch of times. F of 6 here. So when we call a function, every time we call a function starting at that point, the return value is always going to be the same. Every time we call the function, it's going to do a huge amount of computations. If we've seen it once before, we don't need to do the rest of the computations again. If we just save the value, and the next time we see that input value, we just return the output value that's associated with it immediately. But let's start by actually writing this function, f. This function, find that function of n that goes like this. We're going to say, so 2 parts of a recursive function is the base case and the recurrence relation. Base case is when do we stop recursing? We're going to stop recursing when we either get to this point, somewhere over here, or when we touch grass or a flower. So we're going to say if my in is bigger than or equal to the length, we're going to return 0 for there's no way to get to here if we're over here. Does that make sense? Because we cannot go backwards. If n is equal to the length minus 1, which means we're on the last element, we're going to return 1, because starting at here, there's only one way to get to here, which is just staying there. Otherwise, if my array at n is equal to 1, we're standing on a flower, and there is no way to get to the end when we're standing on a flower because we're invalid, we're standing on a flower, we return 0 immediately, which is exemplified by test case 2, which says, or test case 1, I guess, if we jump to here, we're standing on a flower, that's impossible. If we jump to here, we're standing on a flower, which is impossible to get to the end. And we're starting on here, we're standing on a flower, which cannot get to the end. That's what this base case does over here. So now, let's do the computation. My result is going to be 0. And it's going to be the sum of function of n plus 1, n plus 2, and n plus 4. And I could probably just do it here, but I'm going to do it fancily. Watch this. That's some Python magic for you. That one's saying I'm going to take the sum of function of n plus 1, n plus 2, and n plus 4, because everything inside this range. But if you're not using Python, you can just use a for loop or some kind of loop going from 1 to 4, or just hard code function of n plus 1, n plus 2, and n plus 4. That's also fine. One thing I did mention as well is that the number can get super, super big. We have to, this number will get much, much more than like 10 to the 18th, or 10 to the 9th, 10 to the 18th even. We're going to modulo this one by 10 to the 9th plus 7. Modulo 10, 9 plus 7. When you're doing an exponent like this, when you're using Python, you have to be careful not to use this or any other language. That's another operator called XOR, which I think most computer architecture classes might teach, hopefully, or discrete structures for computer science class. And then we're going to return that res. Let's go ahead and code this function. We're going to start by getting the length equals array equals list. Define function of n. Do if my n is greater than or equal to length, return 0. No way to get to the end. If my n equal to the length minus 1, return 1 because we're on the end. If my array at n is equal to a flower, there's no way to get to the end. We're standing on a flower. Result equals sum of f of n plus I for I in range of, sorry, not a range. Like that. Modulo 10 to the power of 9 plus 7. Return that result and print out f of 0. Can I get a first try? I'm a genius. This does not work. The reason this does not work is just because, first of all, there's just too much to do. I'm recursing from 0 all the way to 100,000 because I have in my constraint that my length can be up to 100,000 in length, which is just not good for recursion. Recursion cannot do that much. So where did my code go? We're going to change this one a little bit. Let's do like this. I'm going to set the recursion limit. Python, you can do this one to set the recursion limit. Sys.set recursion limit to, it's like 200,000 just to be safe. Let's see if this works. Where's the code running thingy? Oh, it's queued. Oh, that's interesting. Still nothing, timed out here. And it's still segmentation faults. So somehow this recursion limit doesn't help in this case because we just have too many layers. Two things we need to change here. We need to add the cache, which actually is going to be the one that helps us save the results. Cache in this one is going to look like this. We're going to remove this import sys for now. We're going to use another hash map, another dictionary. And we're going to do like this. If I've seen my in before inside my cache, then I return that cached value, that saved value. Otherwise, I have to do this computation, save the result into the cache, and then return the result. This should help with the speed. It won't help with the recursion. To do that one, I'm just going to kind of like pre-process everything. I'm going to go from length all the way down to 0, and then call the function. And this will just go down the thing, cache the values. So whenever we call the function, we don't have to recurse very many layers. We have to recurse one layer. We're kind of like going backwards. What this one pretty much is doing, it's calculating these ones first. So these ones don't split anymore. And then calculating this one doesn't split anymore, this one doesn't split anymore. It's like doing that pre-computation. So if you ever see that segmentation fault in your Python, try to do something like this. Nice. Last problem. This is the tricky one. This is the most fun one I have to write. I am not actually related to what is his name? John Appleseed. I made a funny name though, because our names both start with J. But clearly John Appleseed's code forces ranking is lower than mine, so I'm superior. How this one works is that we're given a bunch of trees, and I'm going to write down this input: 733, 246. 7, 3, 3, and that 2, 4, 6. What this one means is that I am starting at location 1, and I'm trying to get to location 7. 1, 2, 3, 4, 5, 6, 7. Oops, let's see. I can, what this 3 means? 3 means I have 3 trees. Symbol 3 means I have 3 trees. So my trees are given in this array: 2, a 4, and a 6. And this 3 means I can make a maximum of 3 stops along the trees. Every time I make a stop on a tree, I get to refill my bag of seeds. So how this problem works is that I'm going to start this 1. I need to make it all the way to 7. And for each empty space that does not have a tree, I'm going to plant a seed. I don't need to plant a seed in the ones that already has a tree, because there's already a tree there. But I have to find the smallest bag that allows me to plant a seed in every one of these, making a maximum of this number of stops. In this case, if we just give 1 a try, we can try a bag size of 1. Let's start with a bag size of 2, actually. If we make a bag size of 2, we can plant a seed in this one, plant a seed in this one. But maybe we want to make a refill here. So our bag still has 2 seeds now. Then we're going to plant a seed here, plant a seed here, then we made it to the end with only 1 stop. But our bag size is 2. We can do better with a bag size of 1. Good to go? See you later then. If our bag size is 1, then we can plant a seed here and refill. Plant a seed here and do a refill. Plant a seed here, do a refill, and plant a seed here. As long as we're within this constraint of how many refills we're given, then it's fine. We're just looking for the minimum bag size that works for this. If at last we're given a bag size, maximum refills of, let's say we're given like 0 refills, then we need a bag size of 4, because we cannot refill this one. We have to have enough seeds to plant in all of these ones. That's making sense to everyone, I hope? To actually solve this one, it's a weird strategy. We're going to guess and check. We're just going to try a bunch of stuff and then see which one works. But we're going to do it in a smart way. We're going to split this one into 2 subproblems. One subproblem is called the, I don't know what Frid called it in that algorithms class, like the how far can I go in a car before I run out of gas? And there's some gas stations scattered along the way. And then you can refill at a gas station, of course, but with a minimum amount of refill, something like that. How this is going to go is that we're going to try a bag size. We're going to try a bag size. Let's say I want to try a bag size of 10. We're going to try a bag size of 10. I'm going to change this one to a 1 for good measure. Can I make it to the end with only 1 refill and 10 things in my bag? If we go here, 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 we don't need to refill at all. How this algorithm works is that we're pretty much going to put in seeds into the slots, but if our bag is empty, then we kind of like go back to the last tree and then refill there. And we'll see that one later when we get to a bag size of, let's try a bag size of 5 first. I'm still able to make this one, and I'm going to do like this actually. 10 has a bag size, 10 has 0 refills. I need to change this to 1, I keep forgetting. 5 also has 0 refills. If I just go make a beeline for there, I need 0 refills. How about if we have a back size of 1? Can we make it there if we have a back size of 1? I put a seed here, and when I'm over here, my bag is empty, so I cannot. I have to retreat back to this one and refill my bag. I have to go here, and I cannot plant a seed in here. Then I have to retreat to this tree and then refill my bag. At this point, though, I have exceeded my maximum number of refills. I have 2 refills. So then, that's impossible. 1 is impossible. I'll just give 1 3 refills, because I have to refill it 3 times. What if we try a 3 refills next? Does 3 refills work? 3 means I can plant here, 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 not here, so I have to go back to this tree, grab a seed, refill my bag, and then I'm able to plant here. So 3 has a 1. Then maybe we can try a 2. So 3 has a refill over here on this one. If we try a back size of 2, we can plant a seed here, here. When we get to here, we have to go back to this tree to refill. So now I have 2 seeds again. I can plant in here and here. So then my 2 has a 1. So we're going to go through this list and see which is the smallest number here that has 1 or less refills. Because 5 and 10, they work, but they have too many. We can do better if we have a bag size of 3 or 2. Or 2 lets us still pass to the end while using only up to 1 refill. Let's write the code for this one first. And I'm going to do it just in the editor here. I'm going to call this one destination, trees, and stops. Tree list equals I'm going to call my function define many suggestions for function name, and we'll just call this one greedy. And I'm going to give this one a bag size. I'm going to give this one a bag size of size. And then we're going to do it like this. We're going to start at 1. We're going to try to go to the end. If we run out of stuff, we're going to backpedal to the previous one. And then refill the bag. Refills, so I'm going to call refills variable is going to be equal to 0. I'm going to have my current spot is going to be equal to 0 as well. For this one, it's a little bit easier if I pretend that spot 0 has a tree. Because spot 0 I can kind of do technically like a refill on. Because I start at some number of stuff. Current spot is 0. And then we're going to do it like this. If I can make it all the way to the end with my current bag, then I could just return immediately. The math for that one is a bit tricky. But let's think about it like this. Oops. Starting at this point, sorry, let's start at 0 and pretend there's a tree here. Starting at 0, how many empty spaces are there left? I know I'm actually going to add a bunch more over here just to help us with the math a little bit. The number of empty spaces here is 1, 2, 3, 4, 5, 6, which is equal to the length of this whole thing. Sorry, the total distance of this one. Okay, sorry. Let's go back to 7. 7 is a bit easier. The destination of this one is 7. The number of trees are actually going to be 0, 2, 4, 6. And my current tree index is 0. So starting at tree index 0, there's going to be 1, 2, 3, 4 spots left, which is equal to 7 minus the remaining ones in here, which is equal to trees minus tree index. So my trees is a number of 3. I have 3 trees. Like that. My tree index of this one is 0. If I do the same thing as 2, if I'm at 2, my tree index is 1. So it would be 7 minus 3 minus 1. 4 minus 1, which is 3, so 3 spots left. And that'll just give us a consistent count of how many empty spots there are left. So we can say if the number of empty spots left is if the number of spots left is less than or equal to my current batch size, I'm just going to make a beeline for the end and make no more refills. So we're going to do it like this. If my, and I'm going to call this one my tree index, if my destination minus my tree index minus trees, I'm going to do it like this actually, is less than or equal to my size, I'm going to return immediately my refills. Otherwise, I'm going to start moving to the right and stopping when I need to refill. So I'm going to do like this. While I'm going to go like my prev index equals tree index. I'm going to say while my prev index, while my trees at tree index, that's another part of the tricky one. We have to find, I'm just going to go skip these ones, skip to the trees. So I'm going to try skip to here from 2 to 3. How many empty spaces are in the middle, which is kind of similar to this one. That's going to be, let's see, how do we do this one? We do something like this, 0, 1, 2, 3. I need to work out this example because I don't have this math memorized, but 1, 2. In this one, if I make it to here, there are 2 left. Here, there are 1 left. Or if I make the entire thing, that's 3. So if I increase this index, this would be index 0, 1, 2, 3, and 5. The number of empty spaces there are 3 minus 0 minus the distance of this one. So really it's going to be 3 minus 0 minus 1 minus 0 is the number of empty spaces. So 3 minus 0 is 3 minus, and this is where I'm getting the 1 and 0 and the 3 and a 0. So there are 2 empty spaces there. And if I do 5 minus 0 minus 2 minus 0 for these ones, there would be 5 minus 2, which is 3, so 3 empty spaces. Just like if I do a 5 minus 3 minus 2 minus 1, which is 2 minus 1, which is 1 empty space in here. A lot of math in this one. So when you get the chance, try to do this one at home, figure out the math on your own. But oh man, that's a tough one. Okay, let's do the code. I'm going to keep going until my index is bigger than my size. I'm going to assume I have a full bag, and I'm going to keep going. While trees at tree index minus trees at prev index minus tree index minus prev index is less than or equal to the size. I'm going to do tree index, increase that by 1. At the very end of that one, I'm a little bit out of bounds, so I'm going to decrease my tree index again. But I have to check if I ended up on the same starting index that I started off as, I didn't make any progress. So I'm just going to return immediately, it's impossible. If my prev index equals tree index, then I'm going to return some arbitrarily large number. I'll explain why we're going to use this number later. We're gonna do a while true. Let's print out for size in range. Let's go to 0 through 10. Print I, comma, greedy of size, right? We're just gonna see what it prints out. Let's see if I did it right. Because I don't know if I did. This is a very complicated code, of course. But I think it infinite looped. Great. Oh. It's not infinite loop. I need to use tree list instead. Wow, I'm going out of bounds. While I'm also going to do my tree index is in the range less than length of the tree list. So a very long statement. Cool. I don't think it's working. That's not right. Why is it printing out 0? So inside here, I'm forgetting to increase my refills. Three, 1, 1, 0. Because with this one, if I do 1 refill, sorry, if I have a backslash of 1, I have to make 3 refills, like we saw here. I have to do this, this, this. I have to refill at here, here, and here. If we have a back size of 2, we can make only 1 refill. So we have a back size of 3, as we saw before. On this 1, 5, 8, I cannot make it to the end with back size of 0, 1, or 2. Similar with a test case of this big thing. So now we guess and check. So we're going to go up to the size all the way to the destination. And we're going to say, if greedy of size is less than or equal to my maximum number of stops, let's print out that size and exit the loop. Let's go like this. Made a bit of a mistake here. Why is that? I'll put 4. I get a 3. I don't think I can make it to the end with 3, can I? What's going on here? Already have size, less than or equal to stops. Then output the size, output the stops. What's going on here? And this one, did I have a -1 in here? Is my math wrong? I don't know if my math is ever wrong. Less than the size. We're going to return the refills. Is that one right? Destination minus trees minus tree index. Destination minus trees minus tree index. Let's go back to over here. Let's see what this one prints out. I suspect something is going wrong in here. So 3, my expecting is a 3 for a 4, really. Something's not mathing. I'm gonna have to look back. I don't remember how I did this one. Similar math as what I did before. If it's reachable, looks like there's some code with my reachable that I forgot to do, which should be actually length minus trees minus my destination minus trees minus my let's see what I do here. Let's see, I'm gonna check out how this one works and then I'll try to explain it. Cool, looks like it's working. So I made a mistake with the math for this one because if initially I had just my destination minus my trees minus 3nx, but I had to subtract from my destination as well, also, my current tree. And the math is difficult there, but what I was saying is like, it's pretty much the same as the other one we saw, as the other equation, where it's going to be the 3, my current tree, or kind of like my next tree, minus my current tree, my next tree, my current tree, minus my next index, minus my current index. Math is hard, but I encourage everyone to try the math on your own, see how it works. So let's try that brute force one. And let's see those greens. So we're just guessing and checking, right? We're just guessing and checking which one works, which one doesn't. But uh-oh, what's over here? Runtime error? And a timeout, and a timeout. It's too slow. We're gonna make it faster. When we look at this one, what we had before, let's see, why is this one not working? I'm gonna reset this one. You can see that the more we increase our size, the less this one goes. It's like a gradually decreasing function that continuously decreases. It's always decreasing or staying the same, it's never increasing. So it's kind of like a sorted list. We can treat it as a sorted list. And whenever you have something that's sorted in a list, the first thing that needs to come to mind is binary search. So this is a binary search problem plus a greedy problem. We're binary searching on a function, which is a tricky one. It's kind of like the game where you have to guess a number. I think of a number, if you guess the number, I say if it's lower or if my number is lower or greater than you, then you guess half of that again. We're doing it the same way here as well. So we're gonna do binary search like this. Instead of doing like this, we're gonna make my left is gonna be my minimum bag size minus 1, but my right is gonna be my maximum bag size plus 1. In this case, it's gonna be, I'm gonna call it dest. The reason I'm going to call it dest is maybe I have a destination of 10 with 0 trees at all. Then I have to have up to 10 places to put in the seeds. Actually, I'm going to do a dest plus 1 because maybe I do need that 10. In the implementation that I'm doing, left and right are not valid solutions in that binary search. So these always have to be out of bounds. You can look up some templates of binary search. That's the one that I like to do. I'm going to say my result is going to be, sorry, I'm going to do my middle is going to be left plus r divided by 2. I'm going to say result is going to be greedy on that middle. I'm going to say if my result is bigger than my size, then I'm out of bounds. I need to move it to the left because I'm out of bounds. There are solutions that are better. Interestingly enough, it also happens if we're equal. If we're equal, then we can also try a smaller one because we can try a number that's smaller. Kind of like that, for example, where we had a 3. Let's see. One example here somewhere. A bag size of 2 can also do this one, but a bag size of 1 could do it better, pretty much. If res is greater than or equal to the size, let's try to. Okay, I actually need to think about this one. Is that how we're gonna do it? My res is bigger than the size. Then I'm gonna have to increase my back size that I give it. My stops actually. Left equals m, else my art equals m. Print r. How this code is working is that I messed up a little bit on my initial explanation. Let me explain. If my result is doing a greedy search, a greedy algorithm, on this middle point that I choose, if that middle point, it gives me more stops than I have available, then I have to, the more stops than available, then I need to increase the back size that I have. So I'm putting the L up, so I'm increasing the back size. Otherwise, if my resulting back size is less than or equal to my stop size, I can try a smaller back size because we're trying to decrease this back size as much as possible. So we're gonna try a smaller back size if we can, but if we can't, we have to try a bigger back size. So it should not time limit exceed this time because it should be a lot faster. If not, we'll just use pi for extra speed. There we go, all accepted. That's the contest. There are some extra credit ones on the other ones, but these I've already gone over in SCPE Fall 2023. Factor Mashup and Buffet Raid, some people got these ones. I was hoping that everyone who was able to participate in SCPE Fall 2023 would be able to get these, just as like a little review. But feel free to take a look at these of your own, of course. So that's all the problems. Does anyone have any last minute questions for me? Is everything all set? Does that make sense to everyone? I'll take that as a yes, probably. Okay. This was, feel free to look at the recording again, of course. And we'll call it a that. So, SCPE Spring 2024 is officially adjourned. And we will see you in the next SCPE. I have 10 more problems. That's it.